I want to start this video by talking about an algebra qualifying exam problem that has to do with Galois groups of cubic polynomials. This is Algebra Qualifying Exam Spring 2013, number 5A. And you're asked to prove that an irreducible cubic polynomial, f of x in q bracket x, with exactly one real root has Galois group isomorphic to S3. Okay, so we know that the Galois group of this irreducible cubic is either isomorphic to S3 or A3. How do we know which one it is? We're going to show here that this one real root condition implies that it's isomorphic to S3. So what does that mean? That means that the discriminant of such a polynomial can't possibly be a square in Q. And I want to solve this problem, but I want to do it by talking about something that's actually useful for a much bigger set of Galois theory problems. So before we get into that, let's just think about this example from the previous video, x cubed plus 4x plus 2. So we showed that the discriminant here is not a square, and that the Galois group was isomorphic to S3. This does have one real root. Okay, so how do you see that? Well, it has to have, since the so a cubic has to have at least one real root. If you think about what happens when x is very large and negative, x cubed is very, very large and negative, and the value of this polynomial is negative. When x is very large and positive, the value of this polynomial is positive. So you have to cross the real axis at some point. So you have at least one real root because you go from being very negative to very positive. How do you know that there's exactly one real root? Well, if you think about the derivative of this polynomial, it's 3x squared plus 4, and this is greater than or equal to 0 for all x. So this polynomial is never decreasing. So you start being very negative, you go up somehow, you cross the x-axis, and then you go off to being positive infinity. So this only has one real root because if you have three real roots, you need to come back and cross the axis multiple times. Okay, you can make this into a real rigorous argument, but that's the idea. All right, so suppose alpha is this one real root of f of x. What are the other roots? The roots that are not real come in complex conjugate pairs. Okay, so if you believe this, that's another way to see that if you have a polynomial of odd degree, it has to have at least one real root because the roots that are not real come in complex conjugate pairs. Okay, so why is that true? This is just good review of some things we talked about a long time ago. This f of x, it's in q bracket x, it's in r bracket x. Complex conjugation is an automorphism of c that fixes r. So it sends each root of this polynomial in r bracket x to another root of f of x. So when did we prove that? We talked about this in lecture 16. This is basically theorem 2.4 in Conrad's The Galois Correspondence Notes. Okay, so what are we going to do with that idea? Complex conjugation sends one of our roots to the other. Complex conjugation is giving us an element of the Galois group of this cubic polynomial. Here's the setup. Let's suppose that we have k, an extension of q. Think of it as a subfield of C, where k over q is Galois. So in particular, that means that k over q is finite. We've only talked about finite Galois extensions. Then what we'll show is that complex conjugation restricts to an element of the Galois group of k over q. Okay, so what is true about the elements of the Galois group of k over q that you get by restricting complex conjugation? If k is real, if it's contained in R, then this element is trivial because complex conjugation sends everything in R to itself. So it sends everything in K to itself. So it's trivial as an automorphism of K. But if K is not contained in R, then there's at least one element of K that's in C but not in R. And complex conjugation sends that element to something else. But if you do complex conjugation twice, you end up back where you started. So this element has order exactly 2. Okay, so before I prove this proposition, let me say, how does it apply to this qualifying exam problem? Well, if f of x has exactly one real root, then its splitting field, E over Q, is not contained in R because you have this one real root, and then you have these other two roots, beta and its complex conjugate, and these are not contained in R. Okay, so that means that the Galois group contains an element of order 2. Where do you get it from? It's the restriction of complex conjugation to the splitting field, down to E. So what does that mean? That means that the Galois group of this polynomial, well, it's a transitive subgroup of S3. It's either S3 or A3. And it's not isomorphic to A3 because A3 doesn't have any elements of order 2. So it has to be isomorphic to S3. So that's the whole proof. Okay, so I'll pause and erase, and I'll prove this proposition for you. Let's prove this proposition about the restriction of complex conjugation giving an element of the Galois group of K over Q. Well, what do we know? Complex conjugation, that's an automorphism of C that fixes Q. So you have these subfields. So you have this isomorphism from C to itself. What does it do? It's an injective map from C to itself. So when you restrict down to K, it's giving an injective map from K to something. So it restricts to an injective homomorphism of K into some field. That injective homomorphism fixes Q. So what is that? That's an embedding of K fixing Q. And now we're going to use the fact that K over Q is a Galois extension. Because in the proof of the fundamental theorem of Galois theory, we saw that if K over F is a Galois extension, then the set of embeddings of K fixing F is equal to the set of automorphisms of K fixing F. That every one of these embeddings is actually an automorphism. And that's it. That's the whole proof, because we have an embedding of K fixing Q, so it must be an automorphism of K fixing Q, so it's an element of the Galois group. Okay, so let me point out, it really is important that K over Q is a Galois extension here. I mean, if you think about the three subfields of the splitting field of x cubed minus 2 over Q, you have these three cubic subfields, Q adjoin square cube root of 2, Q adjoin zeta 3 times cube root of 2. And if you take that one like that one that's not contained in R, and you look at what happens when you apply complex conjugation, you get an embedding from Q adjoin zeta 3 times cube root of 2. It's not an automorphism. It really is a map from this field to the other degree 3 extension of Q contained in this splitting field that's not the one that's real. Okay, so I just want to say this assumption really is important here. Okay, so we saw how this proposition pretty directly gives the answer to that algebra qualifying exam problem. Let me point out that this problem that we started with about irreducible cubic polynomials with exactly one real root generalizes to polynomials of higher prime degree. So something much stronger is true. And this is a problem from the fall 2001 algebra qualifying exam, problem number 4. I love this problem, but I think it's much, much, much more work than most algebra qualifying exam problems. So I would not put a problem like this on the qualifying exam now. So what does this problem say? Let f of x be an irreducible degree p polynomial over fq with exactly p minus 2 real roots where p is prime. Okay, so take p equals 3. That's exactly one real root. That's the situation we were in before. We're going to regard the Galois group of f, as a subgroup of SP through its action on the roots of f. So this is just a convenience to say that, okay, the Galois group, we can say, talk about, usually we say like the Galois group of f is isomorphic to a subgroup of SP. Here we're just saying that it is a subgroup of SP. Okay, so part A asks to show that the Galois group of f contains a 2-cycle of FP. And where does that 2-cycle come from? It comes from this proposition. If you restrict complex conjugation down to this splitting field, you get an element of the Galois group of this splitting field of this polynomial over Q. And what does complex conjugation do? Well, it fixes these p minus 2 real roots. You have two other roots that come in a complex conjugate pair, so it switches them. So that gives you a 2-cycle. The first p minus 2 roots are fixed. The other two are switched. So you get this transposition. Part B asks you to show that the Galois group of F is isomorphic to all of SP. We know that it's a subgroup of SP. Here we want to show that it actually is SP. And what I like about it, this problem, is now the Galois theory sort of falls away and this becomes a group theory problem. So I'm going to pause and erase. And just for completeness, I'll tell you a little bit about what goes into the proof here without doing all the details. I want to talk a little bit about what goes into proving the second part of this problem, that the Galois group is all of SP. So what do we know? This is the Galois group of an irreducible polynomial. Not only is the Galois group isomorphic to a subgroup of SP, but it's isomorphic to a transitive subgroup of SP. So what's going on is the Galois group acts on the p roots of f of x, and this action is transitive. So what does it mean for a group to act transitively on a set? There is only one orbit, and that orbit has size equal to the whole set. So that orbit has size p. So the orbit stabilizer theorem now tells you that the size of the orbit, which is p, is equal to the index of the stabilizer of x inside the Galois group, which is the order of the Galois group divided by the order of the stabilizer. So everything here is finite. This is OK. So what does that mean? Well, if the order of the Galois group divided by something is p, certainly p divides the order of the Galois group. So the Galois group is this subgroup of SP that has order divisible by p. Cauchy's theorem says that p is a prime dividing the order of this group. This group contains an element of order p. What are the elements of order p in SP? Well, how do you figure out the order of an element in a symmetric group? You write it as a product of disjoint cycles, and you take the least common multiple of the cycle lengths. So what are the elements of order p in SP? They have to have some cycle length divisible by p. But the only things divisible by p that are less than or equal to p is p. So there has to be, the only elements of order p and SP are the p cycles. And now, this is the part that I would want to avoid on a qualifying exam. You can show that any transposition and any p cycle generate all of SP. But this is not so easy. It's a calculation that you have to do once. So without loss of generality, you can name the elements in the set. You can rename the elements in this set of p elements so that your p cycle is the cycle 1, 2, 3 up to p. And then the transposition that you have, you can think of as being 1 and a for some a between 2 and p. And the idea is if you can show that these two elements generate the elements 1, 2, 2, 3, 3, 4, up to p minus 1p, this is a set that we've already seen generates all of SP. So I think that if you were allowed to use this fact that a transposition and a p cycle generate all of SP, then this problem is not so bad. But if you have to do all this other stuff, this orbit stabilizer thing or Cauchy's theorem, recognizing the elements of order p and SP, and then you have to show that your transposition and p cycle generate all of SP, that's a very significant long calculation. OK, so I'm going to pause and erase, and I'm going to give you part C of this problem. It's not even over. Part C of this problem says, let f of x be x to the 5th minus 9x plus 2. And using parts A and B, we want to show that the Galois group of F is isomorphic to S5. OK, so what do we need to do? Let's assume that we've done A and B. We know that if you have an irreducible degree 5 polynomial over Q with exactly 5 minus 2 with exactly 3 real roots, then the Galois group of F is isomorphic to all of S5. So what do we need to do? We just need to show that this polynomial is irreducible and to show that it has 3 real roots. Okay, so let me say something about this second part. Well, what did we do before to say that our polynomial, cubic polynomial, had exactly 1 real root? Is we looked at the derivative and saw when this polynomial was an increasing or a decreasing function of x. So if you take the derivative here, you get something pretty simple. You get 5x to the 4th minus 9. So this has exactly 2 real roots, right? When x is 0, this is clearly negative. But if you think about what the graph of this looks like, you're going to get, I'll draw a picture. You're going to get something that crosses the x-axis exactly twice. So what's happening is your polynomial is increasing over here. It's increasing over here, and it's decreasing in between. So you know that this is negative when x is very, very large and negative, and that it's positive when x is very, very large and positive. So by looking at what happens in between the critical points here, you can see that this is going to cross the x-axis, and then it's going to cross again, and get exactly 3 real roots. So I love this problem. I think it's really, really good. But I also think that it's too long to be a single algebra qualifying exam problem.